Very good morning, Sanjay. Sanjay, very good morning. You have to unmute your mic.
Sir, I think he's not a co-host.
Yeah. Then he has to be made a co-host. Who is in charge of the technical?
This is Sairam, sir. I made him as a co-host.
Sairam.
Now he
Yeah.
can.
Yeah. Sanjay, you need to unmute yourself.
Yeah.
Yes.
Good
All
morning.
right. Good. Good. So I think we are all set.
Sunil is around.
Arijit is here.
Okay.
Uh,
I had a second
Yes.
assignment.
Yes, we will do that. Good morning, good morning. We will.
Shared them, so that we can have a session. So yesterday we had a lively session or tutorial.
Right. Ritesh was there yesterday.
Right.
Right. So I think everything is going very well.
Yeah.
And, we are benefiting immensely from your lectures and tutorials. So we will continue, and hopefully we will organize a second round soon because we were planning to
That
do
will be tomorrow.
Right. And then maybe given the increasing the interest of participants, because some of my own friends who are teaching in colleges, they are very interested in continuing this activity. So I think we'll all benefit from this, and hopefully in the near future, as a second part of this school, maybe we can focus on something more specialized, like we had anticipated in the earlier occasion, right?
Yeah, Sanjay, unfortunately, I missed the tutorial yesterday. And, these afternoons are a little difficult for me. I have some other engagements at the same time. So I am going to have to miss the tutorials, but I certainly have the benefit of attending all the lectures. We have another 3 minutes to go. Arijit is here, and Arijit will be helping us with the question answer session today. So I think by Monday, Arijit will be making the major announcement, I think, on behalf of the Center for Atomic, Molecular and Optical Sciences and Technologies.
Is it?
We are having, we are completing 1 year in August. So we are having an anniversary colloquium series, and maybe I will ask Arijit and Sunil to make the announcement next week.
Oh, that will be great.
So we will be having some very exciting talks in August. So Arijit, we should be able to make that announcement on Monday, right?
Yes. I mean, we have all the information, and
Yes.
we have been fortunate to curate a very good set of speakers.
Yes. So are you going to be joining on Monday morning, Arijit?
So let me just cross-check. Monday is what date? Monday 26th. Yes. Monday shouldn't be a problem. Absolutely.
You will be joining, right?
Yes.
So what I suggest is that maybe you can, at the beginning of Sanjay's talk, you can make that announcement, share your screen and flash a few slides if you like.
Sure.
And inform everybody about the upcoming event so that people get to know and they save those dates.
Absolutely.
Yes. So we will do it on Monday.
Yes. In fact, I think that week, the colloquium week, will be very beneficial to young researchers.
Absolutely. Yes.
Absolutely.
Yes. So
we have some prolific scientists who are waving talks.
We are designing a nice poster. Sunil is very good at that, and Sunil makes some
Sunil is a wizard, I would say.
Yes, so he makes some very nice posters, and this poster should be ready by this weekend, and we will share it maybe Either Arijit or Sunil can flash it on the screen. We have another minute to go.
Right.
We are mostly ready. So a number of persons have already joined. And I assume there are several who would have joined on the YouTube as well. So, Arijit and Sanjay, it is time now. Do you think we can start?
Yes, sir. Yes, sir. We can start. It's exactly
And
10.
and the recording and everything is in place. So I think that has started. So we are on air. Okay, so very hearty good morning to everybody, and welcome back to the lecture series by Professor Sanjay Majumdar. Dr. Arijit Sharma is also with us today, amongst many others, of course. And we had a very exciting 3 lectures so far. So today's is the fourth one. Sanjay has already introduced the coherent states, the Glauber vectors, and so on. So I request Sanjay to continue from this point. Sanjay?
Yeah. Good morning to everyone. So, Arijit will start, or yeah, I
Yes,
can
yes.
start.
Yes, yes, please.
Yes,
please,
you
please.
can share your screen and
I
start.
share my screen first.
Yeah, you can go full screen.
Now-
Good. Very
Yes,
nice.
yes, perfect, perfect. Please,
Excellent.
Yes.
So, good morning, everyone. So, thank you for joining this 4th class. Today, as it was discussed at the end of the last class, okay, we are discussing the coherent states, and we discussed the contribution from Professor Ray Glover, who got the Nobel Prize in 2005. So there was a similar contributions, though it was not awarded as a Nobel Prize, but I think we are proud to be Indian that Professor E.C. G. Sudarshan, so who's actually original name before marriage is E.C. George, and after marriage he has adopted the Sudarshan's name. So he had equal contribution, the same work. But so there are mainly 3 distinct papers which will be very important to explain this. Okay. So, and it is in that chronological order, it is placed here. But before that, I think one should know little history about that. So I'll not give the detail of the history. Professor N. Mukundan has written a nice write-up, or it was an article written in Resonance, okay, and I'll share the reference for that, okay, and what you will see there actually detailed history of how these things has happened, who has contributed how much, all those things. And what I want to bring without any mathematics, I want to bring to your attention some flavor of that. Okay, so the 3 papers, okay, the one if you see, I don't know, witness, okay, so this is that published, okay, CG Sudarshan paper March in PRL, Physical Research Lab, Physical Review later. Before that, there was a published paper by Ray Glover, okay, in Physical Review. That time it was not ABCD was available. So it was said the quantum theory of optical coherence, okay. And after this Professor Sudarshan's paper, Glover has written one more paper, okay, where he has taken some hints from here and made it in proper way. So let me go little details, and what you'll see that. So let's go back. What we know up to now about the coherent state. As we have seen that when you confine the electric field inside a small space, your electric field is quantized and you will get quantized energy. And corresponding the Hamiltonian for particular level n, if you consider, if it operates on the number state which we have discussed, so we'll get that Hn is equal to ENN. So that is your eigenvalue equation. So that means, so if you can calculate or estimate that number states for all labels of n, what you will get? You will get a complete basis, okay, and that will be defined in the Hilbert space. So this is the Hilbert space for the single mode electromagnetic field, what we have discussed so far. So what we can have it using the identity relation, that because we have a complete basis, we can write that projection operator with respect to that number state. Okay, so that is summation of n equal to 0 to infinity in n. Okay, so that is Kate and Graham. So that will be 1 because we got a complete basis. So we are summing up all possibilities. So that is known as completeness condition. So this is very important. You have to remember. Okay, and these number state, as we said, that the nomenclature also the eigenstate of the number operator. And now what is number operator? Nothing but you can write them in terms of creation and annihilation operator, the A dagger A, and with the eigenvalues, what we'll get is that n times of energy of each photon at that particular single mode. And also we said, okay, using this number state, we could get a coherent state, quantum coherent state, which is nothing but that is eigenstate of the annihilation operator. Okay, so with the eigenvalue alpha, and the form of this coherent state will be this like this. It will be summation of all the number states. And what we have found out that this will be one of the minimum dispersive state, which we have discussed so far in the last class. Now, can we have similar kind of identity or completeness relation from this number state, sorry, from this coherent state? Yes, we can have. So we can use this identity also defined in the same Hilbert space, okay, where we can write that here alpha can take any values. It is a continuous, it can be, okay. So that will be d square alpha by pi. So alpha alpha. So that is a 1 Kate and alpha, and which will give 1. Where this alpha is nothing but, okay, your the real part of the alpha and the imaginary part alpha, you have to just take separately in multiply. Now, what happened that if you use this identity of completeness, what you can write, you can write any state in the Hilbert space in terms of this identity. So what I can do that, I can multiply from the right, okay, the psi state, the Kate psi, and what we'll get d square alpha by pi alpha psi equal to giving psi. So we can find out the new state provided we know this matrix element, okay, between alpha and psi. So if we just able to calculate this, okay, by some mean, then we can construct the psi using this identity. But there is a problem, as we stated that if you consider one more coherent state beta, which is not equal to alpha, then this overlap matrix or the matrix element alpha beta, okay, will be not equal to 0. Okay, So what we see that by times actually when these people who are working on the global and Sudarshan's, okay, Dirac delta function is well known, okay, and well established, okay. Though initially the Dirac delta function was not considered well by mathematicians, but later on by Pauli and others actually made it proper way and it was well appreciated. So then what you see it is actually that Dirac delta function between alpha minus beta. So when alpha equal to beta, we'll get 1. Okay, that you will see from here itself. When alpha equal to beta, this exponent becomes 0 and we'll get the 1. But when alpha not equal to beta, this exponent is not 0. So that means that this alpha and beta is not orthogonal. Okay, but what you see it that we see that the completeness is still hold to write that any arbitrary wave function in the Hilbert space in terms of the complete basis of the coherent states. So unlike these number states who are actually orthogonal to each other, here that coherent states are not orthogonal unless in some way you can make it orthogonal in the sense that which I said in the last class, you make one of them among the alpha beta, one of them is very large, is very small, so that this exponent becomes now minus a very large quantity, so it will be tends to 0. But unless that, in general, this is not true that for alpha not equal to beta, it is 0. That means though this orthogonal relation is not satisfied, but still we are able to use this identity to construct any state in the Hilbert space. This is not, this is called overcomplete in the sense that we have to sacrifice one of the condition to make the completeness. Okay. So this is a mathematical nomenclature. So you can just look at it any textbook. Okay. So that's why it's called overcomplete. Some people are super complete. Okay. Now let's come to the work of Professor Sudarshan's. Okay. So for that, I always advise everyone to go through this nice article by Professor N. Mukunda, okay, in a Resonance paper in 2019. I think everyone will love to read this paper or article. So let's get some gist from part of the gist, okay, where actually this has been discussed apart from other works of the Professor Sudarshan's, okay. So it's about the coherent states, okay. So if you just look at this picture, which is a picture for the interference, where actually what we do, so it is a double slit and light passes through that different slits, okay. Now when it comes out, what will get the interference pattern as you see. So now here when the lights comes out, so that when you see the interference, so there will be correlation between the lights which is coming from the different slits, okay. So that has to be understood to mathematically formulate this interference expression. So this interference pattern, which was explained in the 1962, okay, in one of the conference, okay, by Glober, and the Professor Wolf, the famous Born Wolf, okay, he was attending the conference, and when he came back to Rochester, he was very unhappy and shared his views with the Professor Sudarshan's and asked to look at it again, okay, in the quantum framework. And when Professor Sudarshan did very first work, okay, as you see that this paper was published in the March, and if you Professor Sudarshan PL paper published in April, okay, so it was within a month it was worked out in the mathematics. And what was the mathematics? Let me explain it. So what actually is done, actually, so as I said that, suppose let's say that one slit is at X, another slit is X prime. So when the light is coming out from these two slits, so we need to calculate the correlation between the lights, okay, which you can write in the quantum mechanical framework as a creation and annihilation operator of the light mode or electromagnetic modes, okay. So as we have discussed earlier. So E plus and E minus are nothing but, okay, the creation and annihilation operator of the lights mode, Okay, so amplitude modes. Okay, you can think of it. And so you have to take what is understood. You have to take that expectation value of these two elements, A dagger A or A dagger. Okay, with respect to now, with respect to the coherent state. Because what we want the correlation. So A dagger A kind of is a number operator, but this is at different point. Okay, remember. So that means what we are just looking at, we're looking at intensity, okay, which is originated from the two different points. So that's why it is a correlation, intensity correlation, you can say. So what you can calculate is expectation value of the E minus and E plus, okay, with respect to the coherent state. So here, thing is that as you can look at it, E plus and E minus are not something different. It is a complex conjugate of other. It is a dagger, not plus. It is dagger of this one. So transpose and complex conjugate, as it was A dagger. Okay. Now, what one can do that expectation value of this operator, okay, you can think about A dagger A, okay, with respect to the coherent state, you can write in another way using the density matrix. So that actually, I don't know whether I'll be able to go through in the later part, but this we can do. But this certainly we'll talk about the correlation when we talk about the photon statistics again, okay. Now, this expectation value, okay, we can calculate as a trace of density matrix of this state, okay, the electromagnetic state, okay, and the operator. So that will give you your first order collision. So G11 is the first order collision between these 2 points. Okay. Similarly, what you can calculate, you can calculate second order correlation also. Okay, so here you have to take that 4 different points, okay, and distribute your Bayesian annihilation operator accordingly. And as it was done in the case of first order calculation, the correlation calculation, okay, that we take the expectation value in terms of the density matrix, and then it will trace of the density matrix of this one. So we just define these two correlation function definition, correlation function of intensity. Okay. Now, what is rho? Rho is nothing but your density matrix state represented in the quantized field. So here, what we have it, we already have it that the overcomplete basis with respect to the coherent state alpha. So what we know this that we can write down the density matrix in terms of the coherent states, okay, but we have to just write the one phase vector because this corresponding to the amplitude of this, okay, if you talk normally of the density matrix, okay. So you have an extra factor is the phi alpha, okay, which corresponding to the phase, okay. Now Sudarshan has shown that, okay, that is the contribution what Sudarshan has, that phi alpha can be expressed in terms of Fock state itself, okay, single Fock state, okay. So what just you have to just integrate over all the possible value of alpha. So in that case, what you can write it, okay, that G11, the correlation function is nothing but same form, okay, but now you have taking that rho inside and then take the expectation value. What ultimately you will get the form which is nothing but alpha square, modulus of alpha square, that is alpha star alpha, and which is nothing but intensity of the coherent light, isn't it? That is, if you remember that the way we calculated the number of particle, number of photons available in the coherent light, that is that number operator we have used, and that is that alpha stars alpha, that is actually your alpha modulus square. Okay. So that is the thing which you the coherent correlation function you can define. Similarly, you can define that second order one, which will be alpha modulus of alpha to the power 4. Okay. So this is the contribution which he has written, and once you write it, you see that now the correlation function is, you can express it in terms of intensity, classical feature, okay, of the light. Okay. So that's why that you have some statistical ensemble, you can use it classical way, okay, so that to express this correlation function. So that was the goal for the actual presentation of the Glober in the when you was presenting in the on the meeting. And but problem was that in that earlier paper, what Glober did, Glober couldn't write the phi, okay, using this using the identity, okay, that over complete basis. So that's why he couldn't get that unique value of or unique expression of the phi alpha, which was actually which was a unique work by Sudarshan, who has shown this. It is possible to write it in the using the unique expression of phi alpha in terms of the coherent states. Okay. And later on, that in the subsequent paper of the Glober, which was published in, as you see that, as you see it in November, I think. Sorry, yeah, it was in September. Sorry, September. Okay, again in physical review, where he actually explained that coherent and incoherent state of radiation field. Okay, he has adopted that and wrote it in the fresh way. So that was the excellent contribution of the Professor GS ECG Sudarshan's. Okay. So he has many other contribution. I wish all of you should go through that article by Professor N. Mukunda. Okay, this is nicely written and which has a lot of history of all the people who have been there and involved in different way in physics. Okay. So that's all for that work. Okay, let's come back to our original discussions. Okay, where actually we are talking about the last class. If you remember that we are talking about the properties of the displacement operator. As we know that displacement operator is also unitary operator, and we have expressed that d dagger of alpha is nothing but d inverse alpha, and this is nothing but if you change alpha by minus alpha in d. Okay, and if you write the coherent state, okay, as a eigenstate of the annihilation operator, what you can find out that this a dagger of alpha will give you the eigenvalue alpha alpha. And if we now want to write this alpha, the coherent state, in terms of the vacuum state, we have to use the displacement operator, as you remember. So displacement operator operating on the ground state, or not ground state, yeah, ground state, or you can say no photon state, okay? It will give you that alpha d alpha, sorry, there's a mistake again here. So this will be no photon state 0, okay? So then what you can do that, so you will get if you multiply from the right hand side d dagger, what you will get alpha. And using that, what we got it, if you remember in the last class, that we got that some identities for the annihilation and creation operators, where we showed that operation of this d alpha, the displacement operator, will actually shift that annihilation operator by alpha amount and creation operator by alpha star amount. Okay, and if we can just put alpha by minus alpha, what you can see that you can shuffle this d dagger and d. Okay, and then you will get minus here again. Okay. So if you understood that in terms of the creation and annihilation operator, you could also write this in terms of the canonically conjugate operators like Q and P. Okay, or electromagnetic field. So where actually we have seen that Q is displaced by the real part of the alpha, and similar P is displaced by the imaginary part of alpha. And we have seen some example, okay, how the displacement occurred, and we have given an example with the fiber optics, okay, how this, using the loops we can make the displacement. Okay. Now, I'm coming to some thing. So what I promised in the last class, I'll demonstrate that how this displacement operator can be generated or can be implemented in the laboratory. Okay, but before that, I need to just introduce some things which I'll discuss elaborately in the next class. What is known as squeeze state of light. So far, what we have learned actually from the minimum unsteady dispersion or minimum unsteady relation or minimum dispersion relations that the standard deviation of Q and P or dispersion of the Q and P with respect to the ground state, okay, is same, and that is nothing but h cross by 2, and which is satisfying the minimum unsteady relation that it will be going to the lower limit of h cross by 2 if you multiply them. Similarly, what we saw the coherent state is another state which also behaves like the vacuum state or which like no photon state, okay, and but it has a few photons now because of the alpha structure of the alpha, okay, but again behave like a non-dispersive state, okay, and these two canonical conjugate operator, okay, their dispersion is same and nothing but h cross by 2. And we have demonstrated that using that phase space, where actually this is the dispersion dix for the ground state or no photon state, and this is a dispersion dix for the coherent state. Okay, and what we saw that using displacement operator, you can go from one state to another state. And this radius of these disks are nothing but this amount of the dispersion, that is square root of h cross by 2. Question is that, okay, we got that minimum dispersion. Can we go below that? So whether it's possible, may not be both of them we have to do because it has a minimum, the Heisenberg uncertainty relation has given a constraint that the minimum value have to be h cross by 2. Can we make one of them further lower so that at the expense of the other, okay, so that this relation still satisfies, okay. So that is the case that can we make one of the dispersion is lower than square root of h cross by 2, so that I don't bother about what will be dispersion for that p sector, the momentum sector, okay. I want to make it for the position sector and whether that is allowed or not, okay. So that means we want to squeeze the spread of the that state in the position. Similarly, we can do it for the momentum at the expense of the position. Okay. So whether it's possible, and if it's possible, that will be called squeeze state. So we're squeezing the uncertainty of the either P or Q. Okay, that's important at the expense of the other quantum. Fortunately, what we see that this is only possible in quantum mechanics. Okay, that is because that in quantum mechanics you have superposition relations, and where actually using this example I want to explain you that if you have a two number state, one is 0 and one is 1, that means one there's no photon, another is photon is there. So one is like a vacuum, no photon is like a vacuum, and another is a single photon. If you just make a superposed state out of these two states with a proper coefficient like 3 by 2.5, so what you can check that, you can easily do that, that they are normalized. Okay, these states are normalized. So you just calculate a psi star psi, it will be 1. Okay, so now let us calculate that the dispersion in the quadrature of the Q, position quadrature. So I'm just, you can hear it, you can get it in the literature. That's why I'm using the word quadrature. So different papers is written in the name of the quadrature. Okay. So quadrature is that in the particular dimension of the cube. Okay. So that in that quadrature, okay, that if you just calculate a standard deviation, okay, which will be dispersion, or ultimately you have to calculate variance, okay, which you can write it in terms of expectation value of Q square minus Q expectation value square. And what you can do it easily and find out that it will be turned out to be 3 by 4 minus 3 by 8. So how much it is? It is 5 by 8, isn't it? It is 5 by 8, and 5 by 8 is, sorry, this is 4. This is that means 6 minus 3, 5 by 8. So I did a mistake here. So this is more than half. Okay. So what you see that, so this is more than half. Okay. So this is 5 by 8. But if you calculate P, okay, so I think this notation is wrong. So what you will get 3 by 4. Something is missing. Okay, maybe my choice of the coefficient was wrong. Okay, something is missing. Okay, so what actually you will see? Okay, I'll send you the notes. Okay, that one of them. Okay, either this one or whatever I show it the next one. Okay. Okay, same example. Sorry. I think this is half, this is 3 by 2. Okay. Then what you will see that so you just take this is half and this is root 3 by 2. What you will see that either of the coordinate, I have to check it, okay, that it will be less than half in the unit of h cross. And whereas other coordinate, that standard deviation or dispersion will be more than half. Okay. So what we will see um, so that this psi, whatever is written in terms of superposition of 0 and 1, okay, now you will get one of them, okay, one of them, the dispersion will be less than that is square root of h cross by 2. Another one, okay, that is keeping p quadrature, it will be more than square root of h cross by 2. So what we can see that if we just want to visualize this in that phase space, what happened that now the dispersion in the Q quadrature, it will be shrinked. Okay, it will be shrunk some amount. Okay, whereas the other the P quadrature, it will be amplified. That dispersion will be amplified. So what will we see that Q quadrature dispersion is narrowed down at the expense of amplification of the P quadrature. So what we got that we got squeeze state, which actually we said that it has been used in many experiments like LIGO kind of gravity wave detections experiments, where actually we want to have the position of the atom as precisely as possible, so that this whatever amount of the dispersion which quantum state has, okay, like square root of h cross by 2, we are actually beating that dispersion. We are narrowing down that dispersion so that our accuracy is very good. Okay. And interestingly, you see that if you just sharpen that coefficient, it will not be the same. Okay. So please check it which coefficient will be giving you this one. I'll also send you the correct version. Okay. Anyhow, the theme is that using the superposition of the different number state, what we could achieve that one different kind of state of light, that is twisted of light. Okay, and this is possible only in the case of only in the case of the quantum mechanics, because it supports you the superposition of the different number state of the basis set. Okay, so so it is a pure signature of the superposition phenomenon of the quantum mechanics. So my point, which you want to take it from here, is that if you take only the first excited state of the number of states, okay, that is single photon state, okay, you will not get this one. This is only when you just superimpose this one with the 0. Okay. So that 0 is very, very important. That means vacuum, you can't neglect it here. Unlike in classical case where you could actually neglect the vacuum, here it's not possible. So in the next slide, where we are trying to explain the beam splitter, I want to use that phenomena of the quantum mechanics, that vacuum is very important. Let's look at it. So think about it. The beam splitter, classical beam splitter, which splits the lights. Okay, so suppose if you have a light which is coming E1, what would happen? Part of them will be reflected with the E4, and part of them will go to the E3. Okay, so think about it as a lossless kind of beam splitter. So whatever light comes, okay, it actually divide, okay, in proportion to that whatever transmission coefficients, whatever reflection coefficients there. So depending upon the R, if it is a reflection coefficient, P is a transmission coefficient. At this particular point O, okay, where actually we consider that bifurcation or splitting is happening, okay, we can write that E4, the contribution coming from the reflection is nothing but R times E1. Okay. Similarly, what we can write it, this is amplitude in terms of amplitude we are writing. Similarly, we can write that E3, which is transmitted, is T times E1. Where that from the energy conservation, okay, what we can, our intensity conservation, whatever you say, that the E3 square plus E4 square, okay, should be equal to E1 square, which says that reflection coefficient square plus transmission coefficient square will be 1, and that is true. Okay. So now here, as you see that we are taking the amplitude part. We didn't take that the propagation of the wave part. That is because we are just considering at the point 2. Okay, where you can consider that R and T both are 0. So you can just exponential of the phase terms. Okay, you can put it at 1, and we just concentrate on the amplitude part, and we got it. Now, if I just now express the same thing in terms of second quantization, that means we are in the quantum mechanics domain. Okay, the same electric field we are using in terms of second quantization. What would happen? We will be able to write this in terms of creation annihilation operator. So that E1, we could write it in terms of A1 and A1 dagger. Similarly, in E3, we can write A3 and A3 dagger. E4 also will be able to write A4 and A4 dagger. Only thing is that the commutation between A1 and A1 dagger will be 1. Similarly, for the second and third. Okay. So what actually we could write it, okay, that if you have a light which is we are representing as a creation annihilation operator, here we are just writing the representation A1 for this E1 light in the quantum domain or second quantization form, then what you get A4 is nothing but RA1. Okay, similarly A3 you are writing it as TA1. So now if you just calculate the A dagger for ij, which we supposed to get, okay, delta ij, when I equal to j, you will get 1, I not equal to j equal to 0. Now check that. So we have started with the light, okay. So here definitely it is satisfied that A1 dagger equal to 1. Now does it mean that F4 dagger? So if I just write F4 dagger, okay, then using this relation, what you see, this is nothing but R square. Similarly, if we just look at the commutative relation between A3 dagger, it becomes T square. And if we just do it for this one, A3 F4 or F4 A3, we'll get RT star. So this is not equal to 0. This is not equal to 1. As addition of these two will go 1. Okay. But this is, that means definitely it is, if there is a non-zero T is there, definitely this is not 1. So that means there is something wrong in the quantum mechanical description which you are doing it here. Okay. So which is not supporting that conservation laws. So if we just consider that output port on third and fourth port, which are related, okay, that is actually that means that this whatever light is coming in here and there, using the commutator relations, what you see, they have a relation, okay, and that is a wrong description here because they are orthogonal side, okay. So in the orthogonal side, that is not be related. So what was the problem? Problem again that orthogonal input side of the A1 we didn't consider at all. So we need to consider that what nothing is there means there is a zero state is there, zero Fourier state is there. Okay, that vacuum, the empty state also we have to consider quantum mechanically. So zero cannot be a node as you see in the state cases. So if we consider that 0, okay, what would happen? That now what would happen? You have to consider that the red one, this is coming as 0, but the representation of this vacuum state, we are just putting it A2. Now let us see that if I use the A2, whether the conservation laws or whether the commutative relation which we expected is satisfied or not. Okay. So now you want to see that now in these cases, if you just remember that reflections, okay, and transmission happening, okay, for both the light, okay, even now we are considering vacuum as a light, okay, the photons coming through that, okay, and so E4 is nothing but RE1 plus TE2 now. So whatever is coming from there, okay, transmitted through that. Okay. Similarly, E3, when we talk about, okay, so this depends upon that what phases goes in, okay. So if it is thicker to lighter, lighter to thicker, depending upon the direction of the splitter, which is used as glass and mica sheet. So it depends upon thicker to lighter, lighter to thicker, you get phase changes, okay. So here what we're saying that E3, when you reflect, it get a phase change, okay. So R, that will get minus R. So T U1, which is coming from the U1 side, and from the A2 side, which is minus R E2. Now let us consider that what actually we are stuck in the last case, the commutative relation A4 and A4 dagger. So if we write A4, A4 dagger, now we are getting R square plus T square, which is 1. And similarly, that A3, A3 dagger also will be 1. So that this we can work it out yourself easily and find out this commutative relation is satisfied. Similarly, if we have A3, A4, A4 dagger or A4, A3 dagger, what you will see that it will be RT minus T, RT minus RT. Okay, considering that they are the real. Okay, so then it will be cancelled and ultimately you get 0. So what you see that you will be able to treat, okay, that second quantized form of this electric field from each input port and output ports now. Okay, and if you want to write it in terms of this, in terms of the matrix form, this transformation of beam splitter, what you can write. So you got that E1, E2 is a input port, and you got output port E4 and E3, which you can write in the transformer beam split transformer matrix RT T minus RL, which I am writing is. Okay. Now, once you understand that, I hope you understood that why we require these common zero photon states to explain these physics part. Now let's consider we have a beam splitter which is made using dielectric material, okay, and it has a transmission and reflection properties half. That's 50-50 beam splitter, okay. So that means it is again we are using that lossless beam splitter ideal cases, okay, which is impractical most of the times, okay, but you can try to make as precisely as possible. And you can just say that a reflected and transmitted beam differ by a phase plus minus pi by 2, okay. So that means that ultimately you get the relation between them, okay, that plus minus I. Depending upon, as I said, that whether you are coming from the denser to lighter or lighter to denser, your reflection coefficient, reflection phase will change. So in that case, what we can find out that if I said this is A3, this is, so I just a little bit twisted this one, okay. So here is A1 and A1 and A2 input port, and is A3 and A4 input port, okay. So what you see that what we can write, okay, using this phase shift, okay, factor, the A3 is 1 upon root 2 A1 plus IA2. Similarly, A4 we can write 1 upon root 2 IA1 plus A2. So your I you can take it common, so it will be A1 minus IA2. So which actually you expect. Okay. So here the A4 will be so A1 minus IA2, okay, and here it will be A1 plus IA2. Okay. So what you can see that just like in the last slide, we use the some matrix to transform the light from input to the output port. Okay, so here we can use this some operator because we are using the second quantized form of the electromagnetic field. Okay, so if you use second quantized of the electromagnetic field, we can use a kind of operator here. Okay, and operator here, you just look at it carefully. From this relation, you will find out, okay, has the amplitude, okay, 1/√2, 1 1. So what you see that, so we got that operator. But what you see carefully, this is some kind of rough estimation which you have done, okay? And it is not a, so if you do the B dagger, okay, so what will happen that you will get the both minus sign here, okay? So that means B dagger is not equal to B. So it is actually what we got it from here, okay? Just keep it. So this is input port, this is output port. And so in that vector space, state vector space, you can just write it, okay? So in terms of, so whatever that number of photons coming from input port, either 0, 1, 2, 3, similarly here, whatever number of photons coming from this input port, 0, 1, 2, 3, you can just use them as a state vector, okay? So you can write the direct product of them as a total input port state. Anyhow, we'll come to that later. Now check that since this is not an appropriate one, okay, what we can find out, okay, just we can see that if we use, okay, the 50-50 beam splitter cases, where actually reflection and transmission is probably is half and half, what you can write it, these transformation matrix of the beam splitter, okay, we can write it in terms of A dagger A2, A1 dagger A2 plus A2 dagger in, sorry, A1, or you can write A1, A2 dagger, okay, and with a phase because of the 50-50 beam splitting, okay, pi by 2, and there's I. Okay. Now, if you write it, what you can see that, okay, so you will see that that you will get now the unitariness on the beam splitter operator. Okay, and if you operate it on this input state, okay, like here A1 and A2, okay, so what would happen? You will transform it B dagger A1 A2 B dagger, and ultimately what you see that using this operator, you have to do the little calculation, okay, using Baker-Hausdorff formula, which has been used, okay, showed in the tutorial classes maybe, okay, and then what you can see that using that operator form, okay, you can get that output port is A1 plus IA2, IA1 plus A2. So what you see it here, that what you actually were expecting here, okay, so that you get the output port, okay, A1 plus IA2 and IA1 A2, IA1 plus A2 here. So there is nothing but A3 and A4. So using this form of the beam splitter operator, you could get this one, the exact this one. This one you can generalize it. So depending upon that angle of the beam splitter, okay, we are making it 50-50 and 45-degree angle. Okay, if you make a little twist in that beam splitter, some angle you can generate. Okay, so you can get that this transformation relation, okay, between operated by the beam splitter will be some that angle dependent expression. So it will be A1 cos theta plus A2 sin theta. So that means that if you put theta equal to pi by 4, what you will get 1/√2 convex. Okay, and so what you will see that you will get back the same kind of transformation. So what we can say that generalized form of the beam splitter operator, okay, instead of pi by 4, okay, we will say that this is theta. So it depends upon the theta depends upon what is the ratio between reflectance and refractance and reflectance, okay, and what is the angle, okay, that the beam splitter is lying with respect to the input port, okay. So it depends on all this, you can set the theta. So let's see that what is the action of this beam splitter. So we have seen this that A3 and A4 we can get from the input port. And let's say that first example is that, okay, that A2 has the 0 state and A1 is a 1 state. So this has 1 photon, this is 0 photon. So we can write the input state is nothing but for the first port is 1, second port is 0. So, and this you can avoid that direct product, the notation, okay, just for the writing sake, so that it looks very simple to write, okay. And then what you can see that the first one photon in the first port, okay, we could write that A1 dagger operator on the 0 photon. And what you know that if you have both of them a 0, 0 photon, so there's no photon there, and output also will get 0, 0 photon. Because there's no photon there, means that we will not get anything in output. Okay. At least if you have one photon in a particular port, what we see that will get some difference in the output port. But without any photon, we expect that no photon in any ports, okay, will give you no photon in output ports. So if you operate beam splitter operator on this, okay, what you'll see that we just replace A1 dagger from these two expressions, okay, we just extract A1 in terms of A3 and A4, and what we will find out, this is nothing but A3 dagger plus A4 dagger by root 2. And here, instead of that 0 or the 1 and 0, 2, which is representing that no photons are there in port 1 and port 2, we can write that after it goes through beam splitter, there's no photon will be available in the output port also. Now, if we operate this creation operator on this, what we'll see that the third port got, okay, single photon, and the fourth port also got a single photon, but with a particular probability. That means that you got half, probability is half, to get the photon which was coming from the first port, okay, either in the third port or in the fourth port. So that is actually probability distribution. So if you do the measurement, okay, so you have to do it repeatedly. And for one measurement, you may see that you get that photon which was coming from the first port, you got and get it the click in the third port. At the same time, that when you got a click in third port, the fourth port there will be no click. Okay. Similarly, if you get the click in the fourth port, that time the third port there will be no click. So what you see that if you just take that 100 times measurement of that, the 50 times what would happen, you will get click in the third port, 50 times you'll get click in the fourth port. So that means that probability of getting this state of 1, 0 in the third and fourth ports, okay, that will be half. If you get that heat, or if you want to get the state 0, 1, okay, that will be probability also will be half. And that is actually 50-50 classically also does. If you think about, we'll see that, okay, if you have a classical laser light, okay, you can do it here also, as we know that laser light is nothing but a coherent light, okay, quantum coherent light having the alpha value is very high, okay. So we can check that using a laser also it is true or not, okay. So what we got is that we can get the superposed state, okay, up to a state with a detection probability half in D3 and D4 detector. Okay. So D3, we will put the detector here, and they'll be getting click the half time here, half time here. Instead of that here 1, here 0, if you put that here, you have to put that here 1, here 0. That means second port has a 1 photon, first port has a 0 photon. What you will see that the result which you got it, okay, will be similar, but the phase will be just changed. Okay, so whatever was there in this state, okay, 0, 1 state, it's coming with the 1, 0 state. Okay, so but the thing is that philosophy is same. Okay, so if you have 1 photon in 1 port, okay, that will be actually divided. You can think about it divided in the sense that getting that photon as an output port, the half in this direction, in the transmission direction, and half will be in the reflection direction. Okay. Interestingly, now if you just have the two photon in the second port and zero photon first port, you can work it out for the this case also, two photon in the first port and zero photon in the second port. What would happen? Again, you work it out that these two photon you can write A2 dagger square by square root of root 2, and you get that 0, 0 photon. Okay, and which after the beam splitter will be again 0, 0 in the output port. But this A2 now we can using this transformation A3 dagger, A4 dagger, and what we'll get, what you'll get this state. Okay. Interestingly, you see that now, since it has a two photon in one port, unlike this case, okay, where actually one photon is distributed in the two state, here you get more freedom. You get the probability of finding it in the fourth port, both the photons are available. Okay. Similarly, you will get non-zero probability. Okay, where both the detector got clicked together. Both the detector got clicked together, and here what you will see that again that your third port is clicked by both the photon, where in the same time the fourth port was actually empty-handed. Okay, there's no click there. So you have now full distribution of all possibilities. So your fourth port is populated by 2. Okay, there's a probability of that, non-zero probability. Similarly, you have a non-zero probability of both the detector is hit. Okay, and you also have a non-zero probability that third port is populated by 2 photons. So if you have 2 photon, okay, unlike this 1 photon cases, you have a more distribution form. Okay, so that is very interesting. Unlike the classical light. Classical light, what do you expect that again, like a first case, okay, half of them will go, half of them will go reflectance, half of them will go transmittance. Okay, that is still not working here. Okay, so that's a new phenomena if you have a 2 photon. So you get all possible combinations. Okay. Now, interestingly, if you have both the input ports 1 and 1, what you see that, okay, you get that joint photon detection, that both the detector are clicked by the photon, is that probability is 0. What happened that you will either get both the photon in the fourth detector or both the photons in the second detector. Okay. So interestingly, you got this. Okay. So why this the joint probability is cancelled? That because what would happen here, if you want to understand that that T square and R square both are same, and here that joint one, okay, is actually Q square minus R square is 0 here. Okay. In if you want to analyze this. Okay. Now, most interesting part is that we have to do that experiment, okay, and not all of them have this single photon, 2 photon like this, okay. We want to work it with a point light, laser light, okay. So if you still using point light, okay, laser light, and let's talk that you have a point light, you are shining through the second port. Okay, the first port is empty. What would happen using that displacement operator for the second port and get the 0, 0 again? And after transformation, okay, so you just write it explicitly, the displacement operator, as we have seen that we can write in the 3 factors of exponentials, okay. And if you use the beam splitter, okay, so you can now write that A2 dagger and A1, okay, you can transform it. And after transformation, what you will see that, okay, what you got it that, so you can just work it out. Okay, you got third port, what you will get that you will get again the alpha state, that is coherent state, and fourth port also again coherent state. Okay, but the intensity of obtaining the light in third and fourth port, okay, is divided equally. Okay, so half of the light you will get in third port, half of them will be in fourth. Okay, so that is the beauty of this. Okay, and that actually satisfies your classical idea. Classical idea also, if you have a 50-50 beam splitter, we shine the light, okay, what would happen? You are expecting that half of them are reflected, half of them transmitted. And what exactly you are able to see that you will get that coincidence output, okay, half of them lights, okay, intensity, if you just calculate intensity, okay, so this is alpha, alpha square by 2 and this is alpha square by 2. Okay. So add them up again, you will give alpha square, which is intensity of the input port of this 2. Okay, so you'll get the coincidence measurement. Okay, between these two ports. Okay, and what you get that probability of getting that third port is heated by this light, laser light. Okay, to get that is half and this is half, or you can say that intensity is okay divided. Okay. Now, last statement which I want to put it here, okay, if you have it, both the ports are occupied or you are shining lights from the both port, the laser light, that is coherent light, okay. So what would happen, here also you'll see that using the same treatment, okay, you'll see that you get the third port and fourth port will be clicked together, but the amount will be that here it will be alpha minus beta, here alpha plus beta. And when alpha equal to beta, so the third port will be having empty-handed. So there is nothing will be there in third port. Okay, whereas fourth port will be totally filled. So if you have the same light, okay, if you are bringing the same light in the third and fourth, what happen? What you will get that you will get that both the intensity will go to the particular direction. Okay, that is fourth port. Port will actually be populated with all the photons, okay, whereas the third port will be not having any photon. Unless that you have alpha equal to beta, okay, your third port will not get any photon. So when you will have alpha not equal to beta, okay, you will have that third port also will be glowed by some number of photons depending upon what is the alpha and beta. So that will be alpha minus beta square by 2. That is the intensity of the third port. Okay. So what happened? What you got it in output port? Okay. In the case of alpha equal to beta, that there is no photon in the third port, but fourth port will be populated by 2 alpha square. Okay. So addition of this, the input port intensity. Okay. So using this, this is my last statement. What I am to place it. Okay, I am shooting the time. Okay, so what you got it? We got it that using the beam splitter. So here what we are doing using quantum beam splitter, we showed that what will be the operator form of it, and if you have the operator, unitary operator, okay, you can see that in terms of the single photon, 0 photon, 2 photon, you could get some answer for the output port, which you can try once you have that quantized photon. But still, you can check that your classical ideas of beam splitter is working or not. For that, what you have to do, you have to use the coherent quantum coherent light treatment that is actually for high value of alpha. Okay, high value of the parameter alpha. Okay, it will be actually representing your laser light, classical laser light. Okay, and using that, what you see that the classical idea of the beam splitter is still valid. Okay, so with that, I want to stop it today. And next class, okay, what I'll show that using the beam splitter, this is one of the basic ingredient or basic setup which you require for any kind of experiment. Okay, and using this one, we show that how you can use how you can generate the displacement operator in the next class, along with the slides. Thank you for your attention. I love to have some questions if you have.
Thank you, Sanjay. Arijit?
Yes, sir. I
Yes.
think there are a couple of questions. So the first question is the beam splitter a Hadamard gate itself?
Sorry, beam splitter?
Is the beam splitter a Hadamard gate? Hadamard gate.
You can use it, but so you are going much ahead. Okay, using the beam splitter, okay, which will show that, okay, using the two beam splitter, okay, you can make the Hadamard gauge. Okay, so that actually, I think in future, once we have that lectures on quantum computations, okay, or quantum informations, okay, we'll discuss that. You can make, definitely. This is the one of the ingredient for all the kind of experiment you want to do in the quantum optics. Okay, so I didn't say that you can use that two fiber optics fiber. You can use two fiber and couple them, and that will also can be used as a beam splitter. Okay, so there are different ways you can make the beam splitter. So that is a fiber coupler, you can say that. So one important point is that you are superposing that. So this is one of the why is it so important. You are superposing to do different lights, okay, and channelizing in a different direction, and you are controlling using the parameter of the beam splitter. Okay, how much you want to channel in the D3, how much you want to channel in D4. So that's important. Okay.
Right. Okay. So then the second question is, how do you achieve squeeze light experimentally?
Yeah. So we'll have some experimental visualization like that. I'll try to explain that some of the demonstration. Okay. Like you can, as I said, that you can construct the beam splitter. Okay. Quantum beam splitter. Okay. Using the fiber or using some material. Okay. Dielectric material. Okay. And then what you can have, you can find out what is the ratio of the reflectance and transmittance, and depending upon that, either you use that as few number of photons, or you can use a laser light, okay, and check it. So anyhow, what you see that in the classical beam splitter, what you see it, okay, that if you have depending upon reflectance and transmittance, you got to channelize that output port, okay, with input intensity. So here also what you see that we could explain that using the quantum coherent state. The same result you get here. Okay. So that's the beauty of this.
Okay. I think I don't see any further questions in the chat box. So maybe we can call off it today, I think, in the session.
Yeah, I think that's good. That's good. Well,
yeah,
I think there's one question has popped up.
Correct. One question, final question has popped up. So the question is, can we achieve this result by using a different material, different than a dielectric layer? I think corresponding to the beam splitter.
Yeah, it is absolutely right. Okay, so that you can use so the same thing. Okay, either so let's say you have a 1D graphene. Okay, just an example. Okay, so you can shine the light, okay, on graphene, and you are expecting some result, some kind of a reflection, some kind of transmission. Okay, so you can use that. Okay, so you can use any kind of a material. Okay, now you have to understand that further. You have to understand how the material, what kind of a reflectance or what kind of transmitter is there. Okay, so that you have to understand. So like you have done the Black's laws on things. Okay, where you have reflection, transmission, all those things are there. You could explain these similar phenomena. Okay, using this kind of algebra.
Okay, I think then we are done with all the questions. I don't see any other question in the chat room.
Okay.
Anything from the YouTube? Any question?
Yeah, Salvi, is there anything from the YouTube section, or Uma, anything from the YouTube section?
No, sir. No, so.
Okay.
Not so far.
Okay, that is good. Okay, okay.
So this is very good. I think I would like to say, to express my gratitude also to the participants for the questions that they are raising. There have been a few questions, but very good questions, right, Sanjay?
Right, this is a very good question.
Yes. So I think I will very strongly encourage. I think there is one more question coming up, Parijit.
Yeah, I can see
yeah.
somebody is asking if there are any computer simulations available to visualize this mechanism better.
Yeah, so very good questions. So it reminds me something. Okay, so computer simulation using this, you know that random walk kind of problems, okay, which is very popular nowadays. Okay, you can simulate, okay, random walk kind of problems using this beam splitter. You can arrange the beam splitter sequentially, okay, either in the particular 1D or 2D lattice kind of things, okay. And what you can show that simulate it, that after a few steps of the walk, okay, what you can see that whether quantum phenomena is achieving or still classical phenomena. So you could see that whether you are getting quantum random walk or not. Okay, there is a very good paper by Professor J. Sagar and Pathak. Pathak is in, I think, IIT Mandi. Okay, so I think that is in PRA. So that gives very good simulation work. Okay, and there are subsequent work based on that also. So that will be, that is a very good opportunity to test these principles.
Okay. And I think there's one final question which says, how do we calculate non-locality experimentally?
Oh, non-locality experiment. Okay.
Right.
Using this?
I assume he's referring to whatever the.
So there is a question from outside?
Yes, this is a question. How do we calculate non-locality experiment?
Okay. So here I think that the non-locality means that he wanted to mean that that measurement between the coincidence measurement between D3 and D4. Actually, what would happen? We are not when you are talking about that getting the signal in both the port together. So how to know that they are together? For that, actually, you have to bring that, you put that photodiode in the both the port, okay, and bring that the current from both the port with the same kind of cable, with the same length, everything is uniform, and then couple them. Either you add the current or you subtract them, which I'll discuss in the next class. That how to check that. That is called, we will actually do homodyne kind of experiment, okay. Will demonstrate, okay. Using that, you can check that whether coincidences happened or not. Okay.
Right.
So for that, actually, what you do, you need one more beam splitter, okay, and then check it, okay. So which we are not working as a non-locality in the sense that we obtain it here and we obtain here, and we are trying to say that at different position, what we got that photon, okay, and we are saying that we are matching them, okay. We are bringing them to the same point, and then we are matching, okay. So that actually, for that you have to just wait tomorrow's class, okay. So we have Alexander kind of experiment.
Right. So I think maybe you will also discuss about these heterodyne and homodyne measurements at some point, right? So I think we are good and no more questions. So Deshmukh sir, can you please?
Yes, I think we are good.
Yes.
We had a very interesting question answer session as well, and thanks to the participants and the whole team which is making this series of lectures possible. Sanjay, we are really very grateful to you. This is a very nice set of lectures, very insightful into all subtle details of quantum optics. This is a wonderful course, and I'm glad that there are people who are benefiting from it, and all of us are learning new things in this course. So thank you very much. So Arijit, we can close the session, I think.
Yes, I will like to thank Professor Sanjay Majumdar once again on behalf of all the participants and our organizing team for giving us this opportunity to conduct this special course on quantum optics. And we will look forward to his participation in the near future in some specialized topics as well.
So we meet tomorrow now.
Tomorrow.
Once
Yes.
again at 10 o'clock in the morning. So
Yes, we'll meet
So
tomorrow.
just to remind that I think participants, if they can look at the assignments, okay, it will be useful for them. Okay.
Right, right.
Yes.
So we have uploaded the second set of assignments today.
I think so.
Yes, yes, yes. So we will discuss it tomorrow afternoon in the assignment section. Yes. Okay, okay, thank you. Thank you.
Okay. Goodbye, everybody. Thank
Goodbye,
you, Sanjay.
goodbye.
Thank you, Arijit. Goodbye.
Thank you, sir. Thank you.
See you tomorrow.
See you.
Goodbye.
See you. Goodbye.